Today's Tech20 is, you've already had the 20 minutes of your lunch, and now we're going into the 20 minutes of a presentation by our esteemed colleagues from the nuclear industry. And we will then go on to 20 minutes later up to 20 minutes later for question and answers, which I'm sure you'll have some for our colleagues. So why have we invited our colleague Professor Stephen Jones from the National Nuclear Advanced Manufacturing Center, which is part of the Catapult Center, which is there are 7 national Catapult centers in the UK, and it's a research outfit in partnership with University of Sheffield. And the reason we've invited Stephen here is because, similarly with the nuclear, with the decommissioning side of oil and gas, we have a lot of synergies with the nuclear industry. Nuclear industry is very much similar to us. We've taken some lessons from them in areas of asset integrity, late life management, and developing new techniques for manufacturing technologies for future nuclear facilities, which we are also trying to do with future technologies here. But more than that, we've also moved forward into the energy transition area, and that's something that the the oil and gas decommissioning arena is looking into with much anticipation on how we can repurpose some of our facilities and how we can monitor and capture some of the carbon footprints of our industry. So these are similarities, but Stephen will be talking to us today about the technologies and techniques that they use to advance these research developments. So without further ado, I introduce you to Stephen Jones.
Thank you, Pamela. I think I've got this. Okay, thank you, Pamela. Good afternoon, ladies and gentlemen. Thank you very much for allowing me to come and talk to you about nuclear manufacturing and the challenges that we face within nuclear manufacturing, which should be some synergy between oil and gas. We work in high-value manufacturing areas, safety-critical organizations, etc., etc. So without further ado, I'm going to move on to basically very quickly explain who we are, what we do, and then go into some of the challenges across both fission and fusion. Because Luca has already asked me a few questions about fusion, and I'll put that towards the end. So without further ado, as Pamela says, we're one of 7 centers within the High-Value Manufacturing Catapult. However, we are solely owned by the University of Sheffield. So it's very important that that distinction's made here. We are a non-profit organization. We can make a surplus, but we mustn't make a profit. I think you know where I'm coming from on that. So our goal is that we have 2 strands of which we try and support the supply chain. It's all about supporting the manufacturing supply chain. And we support that through manufacturing innovation and through supply chain development and making sure the supply chain is fit for manufacturing in the nuclear world. And nuclear encompasses decommissioning as well. We cover 6 segments here. We've got new nuclear build. We have plant extension, which some of you will be also familiar with. You're trying to extend your oil plants, etc. This used to be called defense. It gets very emotive. So we call it propulsion and security now, because atomic weapons are somewhat sensitive to some people. So weapons of mass destruction, we've taken those out. Decommissioning and waste, which is primarily what you guys are looking at. My colleague here, Phil Jardine, has spent 25 years, sorry to give your age away there, Phil, within Sellafield, probably the world's foremost nuclear decommissioning section. We also have future technologies, and I'll talk about those as we go through, which is very much associated with small modular reactors and advanced modular reactors. And we have fusion and other technologies, such as the other technologies being the likes of the DUNE project. DUNE stands for Deep Underground Neutrino Experiments, so we start doing work in those areas whereby we need to start looking for fundamental particles, which are obviously subatomic. We have 9 anchor technologies that we deal with. Some of those will come out as we go through, but additive manufacturing through to product and process verification, I even have codes and standards in there. People forget about codes and standards. If you're going to talk about innovation, if you're going to talk about developing technologies, do not forget you will need to have codes and standards people on your side to challenge, to push the technology forward. So engage with them in the beginning if you can. We have this philosophy of trying to avoid manufacturing silos. I'm not here to talk about welding, although I could do for the rest of my life. And I'm not here to talk about metrology or machining. I'm talking about integrating those technologies to make sure that the holistic aspects are covered. And finally, just a little bit about the centre's £40 million capital investment. It's open to you guys if you want to use that as well. And we've had a pre-meeting that we'd like to reciprocate and have some access into your new technologies, like your new domes that are coming along, which is really, sounds cool. And we have 80-plus research engineers now. And I like to think of us as a strange organization with respect to the fact that we are pracademics. We have the academic arm and we have the practitioner arm. I am a pracademic. I started out as a welder on the shop floor. I'm now preaching to those people how we're going to manufacture things and design for the future. So, setting the scene. Back in the 1950s, Calder Hall, and all the way through to where we are today, we're at generation 3. We're working on generation 3 plus, which is basically the evolutionary SMR program. The generation 3 is the large gigawatt reactors. You've heard about Hinkley Point C, Wilfer maybe, and Moorside, but mainly HPC, Hinkley Point Center. That's the large gigawatt under our friends EDF. The goal ultimately is to try and get to generation 4 and subsequently beyond that fusion, because that's the future. I don't want to teach granny to suck eggs, but I'm sure you all know how a nuclear plant works. It's a kettle. It's all it's doing is boiling steam, except we're using uranium to generate that energy. And for those who have been really keen and anoraks amongst you who want to know about how this is generated, Chernobyl was very good. It's been very positive for us on the safety aspects. But if I just explore a little bit more about this large section here, I'm hoping no, it won't. But never mind. This bit on the right-hand side is basically an EPR, the European Pressurized Reactor. If we look at it, there are main components in there that really take a long time. Some synergy here straight away with the oil and gas section, large components, et cetera, et cetera. So, pressurized water reactors, steam generators, typically 15,000-ton presses required to build these structures. And also, they have got to handle 350 to 600 tons of mass. The other side of the coin is that it takes 3 to 4 years to make one of these components. So a very large, safety critical. The incidence of failure has to be probabilistic around 10 to the 7th power in years. So one failure in 10 to the 7th power of years. We can't afford nuclear failures. So, how are we going to do that? How can we start to push the boundaries? We have a conventional layout of how a reactor pressure vessel is actually manufactured. So this is a list of forging items and how the subsequent sequences start to integrate. What you're seeing now on the right is a new methodology developed by Forge Masters under the Simple and Informed Nuclear Innovation Program Phase 1, whereby we're trying to minimize the welds. It breaks my heart to minimize welds, but I know deep down that's where we should be going. So how can I minimize those welds but still be involved with them? And if we start to look at all the setups here, you can see also the actual inspection techniques. So ultrasonic testing, visual testing, radiographic testing, and for those who understand NDT and NDE, ET stands for, obviously, eddy current testing as well. So if we move to this, we have a 66% reduction in weld lines. What we've got here is not just a case of welding them, but how do you get to the stage that makes them suitably usable? So we need to start thinking about machining technologies. Here we have conventional machining, we're modeling chips. There is a reason for that, because when we start to look at decommissioning into nuclear fusion, we need to understand how we can de-chip and decontaminate tritium, which is even more of a problem. However, we're moving to the likes of what we call supercritical CO2 machining. No residue, arguably no waste whatsoever. You literally have the opportunity to use CO2. We're trying to burn it off here now. So here we go. There's an opportunity there. What you're getting at now is a new technology that we're developing. You may have heard of electron beam welding, and you can see here where we can apply the electron beam. This is going through a 78 millimeter wall thickness. We've done 150 millimeter carbon manganese steel quite comfortably and quite successfully in tailoring out the joint. This is our chamber, the largest research chamber in the UK, and this is the typical sequence of events that take place. Now, what we're saying here is not just the actual aspect of the design of those parts, but could we make them out of HIP material? So we have isotropic properties all the way through the structure, equiax grain structures all the way through, giving us much better fracture mechanics, much better response to probabilistic failure. So in effect, we're not just looking at forgings now, we're challenging the forging community to look at powder metallurgy hipping. There's a lot of technology that's associated with that, might find its way into other areas as well. All this is aimed at target net zero 2050 carbon or greenhouse gases, I will say. Now, the eagle eye amongst you would have said, well, okay, if I just go back a sec, these structures are pretty small. They're only 5 meters high. The generation, and I can't share with you for NDA reasons, and that's not nuclear decommissioning or anything like that. It's export control with our friends, because we're working on a project with the Americans, and they see this technology as being useful. So it's really keen to understand that what we've got here is just 2 strakes put together, but we need to do it up to 22 meters. So how are we going to get a structure into a chamber that's 22 meters high? That's the eagle eye amongst you, I'm sure. There's many engineers challenge me. Questions in the back I'm trying to preempt. Well, one way of doing it is a concept that we've devised with our colleagues at ProBeam. TWI, fantastic organization, are already looking at out of chamber. We're going one stage further, where we're not going to be restricted to the type of tooling. So all I will say here is the tooling forms a vacuum that can allow us to pull 10 to the minus 4 vacuum that allows us to do 100 millimeter plus. And it's also non-geometric configured. That means it can do squares, it can do round, it can do dome sections as well. This is concept, but it's been proven on a level by ProBeam. By the way, ProBeam, for those who want to go to Germany at the end of November to see this technology, have asked me to share this with you if you want, and you want to understand a little bit more about electron beam welding. So, what are the benefits of that? Well, in a weld joint, you can see straight away that under conventional conditions in the old way we used to do it, double V section, move into double narrow groove, single groove, and eventually electron beam, no filler metal. So if you then look along the left-hand side, that's the amount of energy just to weld the structure. Never mind preheat and post-heat. That's just the energy coming in. This is the time to produce that weld, one weld, and you can see straight away the amount of mass of filler metal going in, which means you've got to control that filler metal. You've got to have the lot numbers controlled all the way back to source, elements, security back on supply chain. Very, very important. Now, this is where I was hoping that this actually could result in a video, but I might be wrong here. It does. Does it? Okay. Wonderful. It looks like it's going to move. See, I was hoping that these guys could come and actually show me how it works. I only put it together. So it's very important that cladding is one of the areas where we're trying to increase the likes of through life. And do you need to put up to 5 to 9 millimeters of material down? This is a 1.6 millimeter deposit in what we call a 2G or a PC position, if you follow joining science. And deposition rates are quite low compared with arc welding, but it means we get very low dilution. The amount of metal that's mixed in from the base material to the final material is very small, which is very, very important. It means that we don't have to preheat the structure. So we're proving that the hardness values across this, without putting more heat, burning more carbon dioxide to produce more energy to create that heat, is eliminated. So it's a very efficient process to actually create an overlay of the structure that we need to prevent corrosion. It's amazing when you go around the supply chain. They're still uncomfortable about nuclear technology, new manufacturing technology. On the left-hand side, I visited a company about 2 years ago, and they're still welding manually their heat exchangers. We've started to move to semi-automated processes, but this is now what we're looking at. And believe it or not, it's not the welding here that saves the time. It's the metrology and machining and the fact that you can push a baffle or a tube all the way through this baffle in one go with one person, because they're perfectly aligned. And that is what's taking all the time in manufacturing. We took 80% out of one of our supply chain tier 1 members' requirements. 80% to produce a heat exchanger. Not so much about the welding. Well, there are technologies I won't go into now that support that to be moved even faster. Very quickly then, going through the next challenges that we face. These are the Gen 4. So what I've just been talking about is technology applied to the likes of Gen 3+. And it's a very, very conservative industry. But here's the real big challenge for us. On the left-hand side, we've got the opportunity now, or challenge, to manufacture products that are going to produce a lot higher temperatures. So in effect, some of these reactors are actually burning radioactive material in some ways. So there's a program stroke company called TerraPower where they're actually looking at burning plutonium to create energy, which then subsequently decays down to another. They're the real alchemists of this world. So the goal here is if we used helium-cooled or we move to the likes of high-temperature gas cooling reactors, we can actually use hydrogen as a burn-off, as a reduction agent, instead of carbon dioxide and carbon monoxide for making steels. So there's an opportunity there to start benefiting what we call combined heat and power, but applied to nuclear, but also hydrogen generation to use it as another source, moving away from CO and CO2. On the right-hand side, sodium-filled reactors or liquid metal reactors, they're another challenge. How does liquid metal flow around and actually start to cool the reactor? And metal interactions there are very much a different setup. On the left-hand side, how do you get a material that's capable of operating at 1,000 degrees, is irradiation resistant and corrosion resistant, and will actually prevent thermal fatigue failure? Well, we've all heard of the term unobtainium. I'm sure you'll find one of those. But we are looking at high-entropy alloys. High-entropy alloys are intermetallics. Great. You've all developed it. How are we going to manufacture it? Because you can't just simply bring it in and form it and do all these other bits and pieces. So there's some challenges there. For Luca's benefit, we're now doing a lot with our friends at UKAEA in Culham. And the question that was asked, how close are we? Well, we're getting closer, very close, in fact. JET, Joint European Tourist down at Culham. I love doing this with school children, but so I'm not, no, please, this is not meant to be there. But it's great to say that at the core here, we produce the hottest temperature in the solar system. And just behind it, 3 meters away, we produce the coldest temperature in the solar system. So 2 Kelvin, 150 million degrees C. That's not a mistake. That's 150 million degrees C. I'm saying it twice so you can record me. What that means is these materials, and the magnetic field that's there is not just to protect the metals, which would be ablated. They're there to create the extra force required to create this fusion. Taking deuterium, tritium, out comes the amount of energy through the neutrons, and we get an alpha particle. So there is a lot going on in titanium and refractory metal development through what we call EBAM, electron beam additive manufacturing. So that's something that we're working on at the moment. It's not all about being a toroid. Here we have the stellarator. Sounds really cool, stellarator. It's like something out of Star Trek, isn't it? But this one, we design for the structure to drive the plasma. This one, which is the WRX7, is manufactured in Germany, and the plasma designs the toroid. So in effect, nature designs a toroid rather than us confining nature, if that makes sense. What we've got here, and I'll get in very quickly now because I know I've only got 3 minutes left, but on the left-hand side is an electron beam filtering system. We're welding a very thin filter. How many beams do you think we're actually coordinating there? Open question to anyone. Anyone like a guess how many beams we've got welding those sections? Go on. Have a guess. 100? 2? 150 is actually 1. You were very close. Well done. That is basically one beam split and rastered across a program that allows us to build that up and weld it in a manner. It means we've got less distortion. This bit here, which I kind of like brushed over, is more your area, which is decommissioning and waste. Now we're actually doing duplex boxes and seeing how duplex materials, 50% austenite, 50% ferrite, can be maintained. We're actually getting 53-47 ratios, which is pretty unheard of. So that's a duplex box, speeded up fast, I must admit. We don't manufacture it that fast. We put ourselves out of business. And this bit down below is part of the electron beam additive manufacturing process. So that's tantalum. So tantalum, tungsten, refractory metals. Refractory metals basically anything over 2,500 degrees, if you want to go on, that's a guide. So any metal that melts at 2,500 degrees plus, we can EBAM it. And we are seen, and I'm blowing our guys' trumpets, as the world leaders in EBAM, because our friends from America think we're the next best thing to sliced bread. So I'm really pleased that the Americans think that of us. We've also got some great work being done by our colleagues at Strathclyde. What you're seeing here is, we know we've got to move in stages, but ultimately it would be good if we could understand, if as the temperature goes up and we can reduce that cycle time, we can use high temperature ultrasonics. So what you've got here is a robot doing an oscillation, and apologies if you, by the way, I forgot, if anybody's suffering from epileptic response, it can be quite a nasty thing. But what you're seeing here is real time. So the weld is being created. When that's done, there's a time period of which you get up to 150 degrees, and then we look at coming in with ultrasonics to see how the defects are forming. So it's quick to actually try and halt any problem that may occur downstream. The trouble is with heat, like everything else, it's a bit like diffraction. So the shear wave that comes through is distorted by the heat. So sound is distorted by heat within the structure. So we need to offset that and find out how accurate we are by finding that position. We can't wait for it to come down to room temperature. It becomes quite long. It becomes exponential in its thermal response. So it's very important that we try and get that done soon. And Charles McLeod and the team at Strathclyde, if you don't know Charles, I recommend you get over to Strathclyde and start looking at some of the excellent work they're actually doing there. And then finally, something that's close to my heart is we should be doing all this technology assessment based on capturing data and using it for machine learning. So we're looking at the likes of probabilistic kernel learning machines. We're looking at multi-layer perceptrons, artificial neural networks, convoluted neural networks, and moving on to the latest version, which is called capsule networks, looking at vision systems. Vision systems can tell us a lot. So for instance, every time you go for an airport lounge and you put your passport in, you stand there, they're looking at you. That's all using CNN, convolutional neural networks, which now move even faster and more efficient when we create the vectors, looking at capsule neural networks. I love this statement here. So we've got this technology here that's looking now at acoustics. Acoustics were looked at many moons ago, but actually what we've got now is the ability to hear things as they're being formed. And I always use the statement, if your work is doing it correctly and it's telling you it's doing it correctly, don't interrupt it. Work alongside it, but don't interrupt it. And finally, we've got a model now that's being looked at how we can start to predict. So we've got prediction, but the next game is prescribing. So if I can prescribe my properties and tailor them to suit, that is basically it. Thank you very much.
Brilliant, fantastic. Thank you so much, Steve, for that. I think you'd agree with me that that was a fantastic presentation that really brings out the deep science and the deep technology into a very understandable approach.
Thank you.
Yeah, so what we're going to do now is take questions for Steve, and we're going to throw it out to the audience and see if anyone wants to take a stab and ask Steve a question. Okay, brilliant.
I was a bit jealous about the technology. It sounded fantastic.
Thank you.
So this is more like a social question. I, as a few other people, have seen the work that Bill Gates is doing, and rather than going to fusion, he's trying to re-envision the fission reactor. What's your thoughts on that?
It's a very good point. The Bill Gates scenario is very similar to the likes of general fusion, which is yeah. So what actually Bill is doing is backing a couple of horses here. I mentioned the word TerraPower earlier on. That probably is the link that you're talking about. There's a great opportunity. There is a statement that the amount of plutonium that's contained within the American storage is actually enough to power the world for 72 years if we can reburn it. So you can imagine the goal there is if we can find a technology that can start to burn waste into a more amenable waste that we can handle, even if it reduces the half-life by a significant amount, is a way forward. So Bill is very, very good in actually supporting that. But there's also another one whereby you may have heard of general fusion. It's using hydraulics and mechanics. In effect, it's a bit like the NSF using lasers. So the National Science Fusion, the big laser where they're trying to literally hit a hydrogen atom and squeeze it and then create fusion energy. The next one is where a guy is trying to actually use plungers with electromagnetic fields. So they're plunging it down and pressurizing it and creating this temperature. So there's many ideas on the market. All this is all wonderful. But we mustn't forget that the regulator at the end of the day is the person we've got to convince here. But no, a very good question, and one that we will keep a watch and brief on. Does that answer your question? Okay.
Excellent, thank you. Anyone else got any question to ask Steve? Anybody? Okay.
Interesting presentation, especially the last slide where you spoke about how in your decommissioning concerns, you're looking at neural networks and how you can, develop algorithms about that. If you show the last slide, there was an input system, and that one. I believe that's what guides your...
Sorry, which one are you talking? This?
No, below.
This?
Yeah.
Okay.
I thought maybe you could throw a bit more light on what that system is.
Okay. Yeah. This, it's like planting someone in the audience, and that's a really good question. I'm glad you said that, because this is the work of my PhD student that he completed within 3 years. And it came out of I used to work for Rolls-Royce, by the way, so please don't hold it against me. And if you've got any fruit, please take it out the tins before you throw it. The thing here is very important, because a major failure could have occurred in one of their aero engines, sorry, faux pas there, on fuel lines. And it was to do with austenitic stainless steels. And the sad thing about it is that the material was changed because it went to a global specification. And what's really important there is that the specification was within standard, but if you know anything about welding these materials, they can cause solidification cracking. So this was developed basically along the lines of, okay, how many parameters, critical parameters, would be required to generate a prescriptive and a predictive term? So what happens here is you'll get artificial neural networks using back propagation. So you've got your weights, you've got your activation energies, you've got your feeders, and then you back propagate, iterate, etc., until you get an error function that's acceptable to you. However, the problem is with that, it'll only tell you where the error is and whether or not you're going to be within standard. The use of genetic algorithms allows us to mutate that, hence the term genetic. We can mutate that by using other bits and pieces in there, and support vector machines actually are machines that allow us to demarcate good data with bad data. And on the likes of the genetic algorithm, it can spontaneously mutate. So we're asking the program to mutate time and time again. So we get you've heard the term epoch. An epoch is a back propagation, front feed, back feed, and comparison. So that's one epoch cycle. We did 300,000 epoch cycles to get us to an error function of 3%. So no one algorithm, cutting to the chase, no one algorithm is the panacea to your solutions. You have to ask each algorithm to test each algorithm. So this black box, which we actually created successfully on a range of materials, it was only from 0.5 millimeter to 2.5 millimeters in stainless steel, we could actually get a weld that would then predict what the stress concentration factor is at the toe, and we can also predict what the austenite ferrite level is from the classic diagrams that you get. So these are the things that I am really passionate about, that we need to start collecting. And big data is one of these things that we talk about as a buzzword, but only when you start analyzing it and creating these machine learning programs will you get anywhere. Does that kind of like answer your question? I'm always concerned that I go off on a tangent and don't answer your question.
It's in your domain. I am looking to replicate this in the decommissioning of offshore platforms. That's why it catches my fancy.
It can be applied to any industrial practice, any manufacturing practice. It can be applied. You know your data better than anybody. The guy who actually developed that is now working for TWI's their NDT organization. So they're looking at neural net algorithms to predict what the inspection criteria would be. You're welcome.
Excellent. Thank you. Anyone else with a question, Steve? Anybody? Or maybe I'll ask you, Steve.
Oh, no, the lady. Sorry, Pamela.
Sorry. Didn't see you there.
So, on kind of changing the way that you're doing your welding and moving towards more of the additive manufacturing side of things, you mentioned codes and standards at the beginning. So what kind of material qualification program have you had to put in place to allow you to move to that next step? Because that's something that we're looking at in the weld decommissioning side of things, is moving from cement to potential alternatives, but how does the industry therefore qualify that material and then verify that it is at least as good as what we're doing at the moment? So it'd be interesting to hear the synergies in the nuclear industry.
It's a very good question and very apt as well. There is, at the moment, you can use additive manufacturing on what, if you were to go to the ASME, you can use them on non-critical. They have a 10 CFR code, which allows us to do additive manufacturing and bolt that on as a test in a real-time experimental setup. They're on non-pressure boundaries, so they won't interfere with the structure in service. But going back to one of the presentations part about the forging and how we're moving into